Another 1,3-dipolar cycloaddition often involves azides. So azide cycloadditions. So let's look at an azide. Now this isn't just sodium azide. This is azide with an R group on it. In fact, let's pick a specific R group. Let's go with, let's just make it a benzene ring, phenylazide. As it turns out, when you do azide cycloadditions, you tend to not do cycloadditions onto alkenes, but to alkynes. And I think it'll be apparent later why we do that. So let's pick an alkyne that has an R group on it, and that'll be phenyl. And this is actually a pretty common type of cycloaddition that people might do. So let's draw out the azide fully. So we'll have the electrons at hand, and we'll be able to show the mechanism. So N minus attacks. We break one of the pi bonds in the alkyne. It attacks the terminal nitrogen and pushes one of those nitrogen pi bonds onto the N+. And so we're going to get a 5-membered ring if you trace the outcome of those mechanism arrows. We get this as the product. Lone pair, another lone pair, another lone pair, and a phenyl there. And we get this structure. This actually has a name. It's called a 1,2,3 triazole. And unlike what we saw with dipolar cycloadditions involving ozone, the triazole, this particular triazole, is stable. And triazoles in general are stable. So we can form this product and isolate it. And they're really well-behaved molecules. They're crystalline solids. They're just really easy to work with. Now, why is this so stable? Well, because we did a cycloaddition with an alkyne and because of the electronic structure of azide, when we complete the cycloaddition, you'll note that this is an aromatic molecule. It satisfies Huckel's rules. We have 2 electrons in this pi bond, 2 electrons in that nitrogen-nitrogen pi bond. We pick up another 2 electrons for that nitrogen lone pair in the p orbital, and we get 6 electrons total in the pi system. It's an aromatic molecule, and it's stable. And in fact, these types of azide cycloadditions have become extremely popular in chemistry. These kind of cycloadditions are very easy to perform. People often, and most often, add catalysts to these reactions to make them a little bit faster and to control some of the outcomes of the reaction. But they're all over the place. In fact, they've been found to be really cool ways for biologists to do simple chemistry. So you might have a protein, and you might take that protein and attach it to an azide, and then you might have some other molecule, and you'll attach this to, I don't know, some molecule. Hard to be more vague than that, but some molecule. And what you can do is by doing this cycloaddition, you will connect with a triazole ring your molecule and your protein. And you know what? It's kind of hard to connect molecules to proteins. It's just one molecule. That's a hard thing to do. So, but this chemistry works so nicely, and azides actually are pretty well behaved in the body, and so are alkynes. So this sort of chemistry has been used a lot, and I mean like since the year 2000, people use this all over the place. So if you see much chemistry, hear people talk about their chemistry, you will encounter people talking about 1,3-dipolar cycloadditions, and in specifically, they will talk about doing azide cycloadditions often as biologists, and they're connecting proteins to different molecules to see how they behave once they're in contact with each other. So it's a super useful reaction, and it really arises because this 1,2,3 triazole is a stable aromatic molecule.